Hello, this is Dr. Glasbrenner from George Mason University, and in this video, you will learn how to formally conduct two-sided hypothesis tests using the infer package. If you would like to follow along with the examples shown in this lecture, you can load the dataset directly from the internet by placing the following setup code block at the top of a new R Markdown file. This will load the tidyverse and infer packages and load the college applications and gender discrimination datasets directly from data.cds101.com. The code block below recaps the two different null distributions we simulated in the previous lectures for this module. The first chunk of code simulates the null distribution for the college applications dataset, and the second chunk of code simulates the null distribution for the gender discrimination dataset. We will assume both of these simulations have already been run in all subsequent slides. Here we introduce a stricter form of the hypothesis test called the two-sided hypothesis test. It is stricter because it expands the definition of which values are the same or more extreme than the observed value in the null distribution. It also means that we are answering a different research question, which impacts the way we phrase and formally write down our alternative hypothesis. Let's consider an example. In the college applications dataset we considered in the previous lecture, let's see what happens when we modify the research question to the following. Do the data provide convincing evidence that the average amount of schools that GMU students apply to is different than the national average? While this does not change our null hypothesis, h sub 0 colon mu equals 8, it does change our alternative hypothesis, which we write as h sub a colon mu not equal to 8. Before, we were checking only if the average number of applications was greater than the national average. Now, we are checking if it is either greater than or less than the national average. The above is an example of a two-sided hypothesis test. In principle, the p-value of a two-sided test can be different from a one-sided test. Computing the p-value of a two-sided hypothesis test is simple to do with infer. Just change the direction keyword in the get_p_value function from right to both as shown in the code block below. The visualization of the two-sided hypothesis test looks like this. The histogram showing the null distribution is the same as before, but with the two-sided hypothesis test, we now see two shaded red regions instead of one. Like before, the p-value is 0, so moving to the two-sided test has not changed our calculated p-value. For a significance value of 5%, we reject the null hypothesis and conclude that the data provide convincing evidence that the number of schools GMU students apply to on average is different from the national average of 8 schools. Let's consider a second example. We can use the same null distribution that we generated earlier to compute the two-sided p-value for the gender discrimination experiment. Conducting a two-sided hypothesis test for this experiment means we are counting when the difference in the men and women hiring fractions is larger than 0.292 and also when it is in the opposite extreme, which would be when the bias is towards hiring more women than men. We take the code we use to calculate the one-sided p-value and make a single change. We set the direction keyword equal to both. We obtain a p-value of 0.0486. This is smaller than a significance value of 5%, so again, we reject the null hypothesis and conclude that the data provide convincing evidence of gender discrimination in promotion decisions. To create a visualization for the two-sided hypothesis test, we take the code we used to create the visualization last time and change the value for the direction keyword in shade_p_value from right to both. Everything else we can leave the same. Like in the college applications example, our null distribution visualization has two shaded red regions on it instead of one. These regions indicate which parts of the null distribution contain values that are the same or more extreme than the observed value.